Okay, so now we'll shift gears. Talk about transformations. Okay, I mistakenly stopped recording the video, but now I've restarted. Okay. So let's talk about transformations. Sometimes you look at your data with EDA. You should always do this first, and this is a really important thing to keep in mind next year when you're doing your honors thesis. Your professor, or your supervisor, your advisor, whatever you want to call us, is going to want to see the data in a summary kind of form without any stats done. Just see some graphs, things like that, just so you can look and see. You should just do that for your own work, always. And you see a nice big difference, right? So you see some beautiful, you graph this stuff up, and you see, I don't know, something that looks like this. Big difference. You go, well, there's obviously a difference. You do your ANOVA, and what you get is nothing. It says, what F is 1.3. That's not significant. But there's a difference. What's going on? What's going on? Perhaps you violated an assumption. And if it's an assumption that we can kind of deal with violations of, it's fine. If you violated independent events, that's a non-starter. You should go do the experiment again properly. Or do some incredibly complicated math modeling. So go do the experiment properly. It's an easier thing to do. But in random sampling, I've told you before, not a big deal. The one is usually variances, right? It's almost always the variances being way too different from each other. Okay. Like that? Is good, eh? Transformation there. What can be done? Well, we transform our data. So we re-express our data using a mathematical operation. We don't lose any of the richness in our data. We don't lose any of the... We can easily get the original data back. So we do some mathematical operation on it. You say, like, multiply them all times 4. Subtract 6 from all of them. Well, subtracting 6 from all of them is probably not going to do anything to the variances. Multiplying is going to do something, though, isn't it? Or other mathematical operations. And you might think to yourself, well, that doesn't seem fair. You can just do it. You've got a bunch of numbers, just change them. That seems like cheating. No, cheating is when you use your phone in a test and I kick you out of class and give you an F for the course. Sorry, that happened this week, on Monday.
Again?
Yeah, again. Spread it around that I don't take shit like that, so I don't have to deal with this garbage anymore, please. Like, get it out there. I don't care, by the way, if you say Andy's an asshole. I don't fucking care. I just don't want to deal with this anymore. Okay, sorry. Shouldn't have swore there, but I'm really getting annoyed. You guys are great, by the way. You guys are awesome. There's no issue with any of you guys. It's a joke. It's totally a joke, okay? You just look like you can take a joke. I'm sorry, I completely destroyed you or something. Okay, good. I don't want to wreck anybody's whole self-concept, which really says something about how much I must think about myself, doesn't it? Oh, he doesn't think great of me. I hate myself. No, don't think that. I'm saying that to myself. Don't think that you're so important that people think like that about you. You might think that's not fair, and I might say, of course it's fair. It's fair like this. What's the temperature outside?
Cold.
It's minus 12. Minus 12, something like that. It's also, what's that, about 18 in those Yankee imperialist running dog lackeys of the landowning class degrees? Sorry, I'm probably talking like North Korean for a second. Anybody? Okay, so Fahrenheit and Celsius both measure temperature. They're fine. They're fine. You may not like Fahrenheit because you use the Celsius. You may not like Celsius because you use the Fahrenheit. Right? You may like centimeters more than inches, but they both measure the same thing. They're fine. Right? We changed to metric in this country when I was in grade 4. So for up until grade 4, I learned about feet and inches. I learned about gallons and pints. And then they said, oh, you don't have to know that shit anymore. It's all meters and stuff now. Okay. So people my age, basically, sort of older Gen X people, we're just confused about units of measurement. People older than us can do all the imperial ones. People younger than us can do all the metric ones. People like us are going, I don't know. I don't know. And that's why people measure things with, how many football fields is it? Things like that. All right. All I'm saying is these are just different units. That's all they are. Just changing units. You know, we can't just randomly change things until it works. We have to, we need some guidelines, okay? So, the first one thing you can do mathematically is you can take a logarithm of a number. We've talked about this before. It pulls down big ones much more than small ones. So if you think about it, like the logarithm, and I'll just use base 10 logs because it's easier to do in my head. So if we had a bunch of numbers here, so if you have the number 1, 10, 100, and 1,000, if we take the log of 1, it's 0, the log of 10 is 1, the log of 100 is 2, and the log of 1,000, which is 1,000, is 3. Okay? You might look at that and go, huh? Well, it's 10 to the exponent of 10 cubed is 1,000, 10 squared is 100, 10 to the 1 is 10, and anything to the 0 is 1. Right? Anything to the 0 is 1. Remember that? You can't do negative numbers. You can't take logarithms of negative numbers. You see what it did though? It did very little to these two numbers. Look what it did. It pulls 1,000 down to 3. So it pulls up big numbers way down. So if you've got a lot of variation, like maybe this error bar here is like that, and the other ones are small, that looks like a candidate for a log transform. Okay, so it's just logarithmic units. We have a lot of things that are logarithmic units. Right? The Richter scale, you know, for earthquakes. A earthquake of 5 is 10 times more powerful than an earthquake of 4. An earthquake of 6 is 100 times more powerful than an earthquake of 4. An earthquake of 7 is 1,000 times. At 8, you don't want to be around when there's an 8. Like a 4 you would feel. You would feel a 4, especially we would because we aren't used to earthquakes here. But going up by 3, we would probably all be dead because we're in a building that likely wasn't built with earthquake standards because we don't have earthquakes here. Decibels work the same way, right? So 70 decibels, which is probably how loud I'm speaking, depending where you're sitting. 80 decibels is 10 times louder than that. 90 is 100 times louder. 100 is 1,000 times. So, and 110 is 10,000. 120 is 100,000. 130, which is the threshold of pain, is 1,000,000 times louder than what I'm talking about right now, which is at 7. Logarithmic units are a thing. We use them. Okay? If they're not weird. Remember log scales about a few years ago? Remember there was a thing that happened where we all got sick and a bunch of people died? Remember looking at graphs of cases of COVID-19? Remember this? It's like, oh yeah, it's fine, it's fine, it's fine, it's fine. Ah! Exponential growth, right? If you take logarithms of that, you get a straight line, which makes it easier to play with mathematically. For most people. Okay? This is why people have had trouble understanding. I remember we canceled a conference. I was going to go to Florida for a conference. They had 2 cases in Florida, and we canceled the conference. People were like, there's only 2 cases. It's like, yeah, but see exponential growth, there'll be 40,000 there in 2 weeks. Okay? And I don't remember, but if you're anything like me during this, I was, during the whole thing, looking at data, I was trying to see what's going on, and looking at the doubling time, and that's, again, logarithmic growth. So we're going to take big numbers and make them much smaller than what happens to small numbers. Like I said, logarithmic scales are a thing. We use them all the time. Reaction time's another one. It's got an exponential curve. Okay, so think about this. If I was giving you drinks of alcohol and measuring your reaction time. Your reaction time goes up with your drinks. And it goes up like that. And you know this, right? Anybody who's, unless you don't ingest any psychoactive drugs at all, which I believe is none of you. No, because somebody here, there's always somebody, I don't know anything. Caffeine? Most of us ingest something. Anyway, alcohol though, or cannabis too, you get pretty bad with your reaction time after a certain point, and it gets really bad. So reaction times are very often just log transformed right away. Now you might say, well, Dave, you said you can't take a log of a negative number. No, you can't. It's just add a constant. So let's say your lowest number is -3. Just add 4 to all of them, and then take the log. Okay. Questions? So that's one way to go. So it's log of x plus y. In that case. What about a square root? Okay. If you have counted data, I'm not going to go through why this is the case, because it doesn't matter. When I say counted data, how many people are doing this and how many people are doing that? How many correct responses? Things like that. Can sometimes show problems with variances. It tends to do a weird thing where it makes the means proportional to the variances. So if the means double, the variance is double. So what you do is you take the square root of the number, and if it's a negative number, you just add a constant again. So you can take square roots of negative numbers, but they aren't useful for our purposes, right? The imaginary numbers, they're great in electronics and stuff like that, not much use for us. We were learning that the square root of -1 was I. Oh, okay. We just gave it a name. We should have called it like Steve or something like that. Because calling it I was a choice. Like, we're just going to call it I. Okay. So we'll add a constant first if we get a negative number, because we don't deal with imaginary numbers in what we do. Reciprocal, I love, this is my favorite one. We all have a favorite transformation, I'm sure. This is the easiest one for me to understand. Maybe the log is. But anyway, just take the reciprocal, which is just flipping the fraction over. This makes the range smaller. So if you've got a bunch of big numbers, well, again, looking at our numbers here, 1, 100, 10, 100,000. Now our numbers would be 1, a tenth, 100th, and 1,000. They all go between 0 and 1 now. See how much the range just got smaller? And you're thinking, but Dave, you can't just take the reciprocal. Yes, you can. First of all, the numbers don't know what you're doing to them. They aren't going to complain. No one's bringing you up on charges at the Hague for torturing data. This is really good with latencies. And in fact, it's done as a matter of course with latency. So that's just elapsed time after a task has begun. You think, well, that doesn't seem right. Let's see. Time to finish something, or speed, which is the reciprocal of, oh, okay, yeah, it's actually, it's just, you're just measuring now speed instead of time. Kilometers per hour, hours per kilometer. Oh, okay. It's fine. It's totally cool to do this. Just turns it into speed. You're turning time into speed. It's not magic. It just, it tightens the range up. There's a very famous paper in animal learning about, and it's about, I'm not going to go into why, but it's about the latencies to run down an arm in a maze. It's from about 1968 or something. And the person who did it, Abe Amsel, big deal. He did exploratory data analysis, said this group is taking longer, and he did the ANOVA, nothing happens, did it. And then my stats professor actually said to him, hey, I taking the reciprocal of that. And he did, and it was fine. Everything worked. Right. So you do that with latencies almost as a matter of course. You turn them into speed. This is the weirdest one because you have to try to remember some trigonometry. Well, you have to remember what trigonometry is. You have to actually do any trig. I love trigonometry. Wasn't it cool? Like, just it was kind of logical problem solving. Yeah, some of you are nodding, some of you are acting like you're going to throw up your mouths a little bit, so it's a bit of both, right? I love trig. Trig and analytical geometry, right? Like the angle side angle theorem and all that stuff. And you like, prove that this angle equals this angle. You didn't like that?
It's the only reason I passed the grade 11.
I loved doing those. They were my favorite thing in all math, was doing analytical geometry. Because they were puzzles. Just puzzles. Okay, with proportions, so percent correct. We use percent correct a lot in psychology. The kind of stuff I do, we use percent correct all the time. So what this does is it stretches both tails out. So when you're using proportions, there's going to be more variance if just think of this, it's percent correct. Yes or no, okay? If the average of a group is 50, their variance is going to be a lot more than a group whose average is 0 or whose average is 100, isn't it? Does that make sense? Because if you're getting close to 100, you're getting close to 100 all the time. If you're getting 50, you might have 70 and 20 and 35 and 65 and 52 and 48 and 99 and 1. I think those all average out to 50. Very spread out. What the arc sign does, which is the inverse of doing a sine, is it stretches both tails out and makes the middle go down. So it just pulls the distribution out, makes it more uniform. Okay. So what you actually do, it's not just the arc sign. You take the square root of the original data, of the original values, and then you take the arc sign of that, and then you multiply that times 2. I don't know why, but it works. So the cool thing about this is a lot of times you'll find with things like proportions, percentages, and again, we use these a lot in psychology, like a lot. At least one of you will certainly use some kind of proportion or percentage next year in your honors thesis. We love percent correct. It's something we all like because it's like, oh, how many words did you recall? Or how many of this did you do? How many of this happened? We're always doing that. What proportion? And you'll find, I didn't find a significant effect. And next year you'll be practicing your honors thesis talk. And if, depending on who your advisor is, because if it's me, you would have already done this. Some people who are less into this crap than I am don't just memorize these things because their brains work like that. This isn't saying anything bad about anybody except Wayne. I'm kidding. Always happens. People practicing their honors thesis talk and they go up there talking, and we listen to your practice talks. Like it's like a whole thing for a couple of weeks to make sure your talks go well. And we help you, give you tips. And always somebody says, I didn't find anything, but you can see that it looks like it's approaching significance. And after the end, my 2 questions are always this. Why are there no error bars in your graphs? That's the first question. The second question is, why did you not transform those? Like the arc sign transform, right? Remember I taught you that last year? Yeah, this person just said yeah. And then very often they go and do it, and then it works. Now, I will say that sometimes my students forget to do it. An old student, I've told you about Shauna, the student I had that did her honors thesis on swearing. But she swore more than me, it was great. She starts emails to me with, her salutation to me is, fuck off, I fucking hate you. That's it. She's graduated. And don't you start talking to me like that. But, again, you guys are cool, no problem. But, so she does this thing, and she couldn't find anything. And it really looked like she found something. So, I said, why didn't you transform your data? And of course, when we're practicing, she said, my advisor didn't tell me to. I said, your advisor told you to do that in third year. And of course, she replied with, F off, I hate you. The fun thing was, I then gave her a paper of mine to read just to do some comments on, because you do that. Just, somebody take a look at this. And she said, the only reply she gave, where are your effing error bars on your graphs? And I replied, I don't need them, they're counts. Oh well. I enjoyed that, just Shauna was great too. Pretty easy transformation. Because SPSS will do these things for you. There's even a menu in SPSS about transform. And you just create a new variable and tell it, oh, I want 2 times the arcsine square root of this, and it does it. But this is not hard to do with the computer all. When do you transform your data? Not every chance you get. One of the things that people sometimes get the wrong lesson, sort of the wrong message from this quick lecture is that I should be transferring my data as much as possible. No. No, if you can not transform your data, it's better because your audience, be they readers or listeners when you're giving a talk or something, your audience is always going to understand the original units better. So I know what 100% is. It means perfect. I know 0% means horrible, and 50% if it's 2 choices is chance. I know that. I can think like that. I don't know what 2 times the arcsine square root of 100 is. I just don't know. So I don't know what a good score looks like when it's transformed. I just don't know. It's typically something you use when the variances are messy. To pick a transformation, these are rough guidelines, by the way. There are other ones. These are the most common ones I've talked about today. I don't have these memorized either. I don't use this information very often. So I have gone back to this lecture, to my slides, and said, okay, what? Oh, right, that one. The only one I remember is 2 times arcsine square root because of these portions all the time. If your data don't violate any assumptions, transforming them won't fix anything. It'll just confuse you. So if you haven't violated the homogeneity of variance assumption, which is always the one we're trying to fix here, almost always, if there's nothing there, there's nothing there. Okay. So you may have to do it, but you got to be judicious with it. All right. Are there questions about this stuff? I will, by the way, never, ever, ever ask you what transformation did you use in this situation. Because like I said, I can't do that on the fly. I can do it by looking something up, because I know I have a lecture that I've prepared, and it's right here. But I wouldn't, except for the arcsine square root one. I know that one, but I'm not going to, again, ask you, who's that? I just wouldn't do that to you. It's literally the kind of thing people use textbooks for. And that's why we all have stats textbooks on our shelves. You might wonder, you're not taking stats anymore? Well, we all need them now and then. Hopefully we all know how to do a t-test or something, know the formulas, but like all the stuff I talked about today, again, same with the post-hocs. Nobody knows these formulas, usually. All right, questions on this stuff? Okay, I want you guys all to have a great break. Well, you should try to get it caught up with your work and all that stuff because it's technically you're supposed to do. Also, please take some time for yourself. It's important that you take, even if it's just a day of doing nothing, do that. And if whoever says you can't, if let's say you're going home and your mom and dad say, no, you should be doing this, say, no, my professor said I should relax. All right, thanks guys.